really normally only used at the end of fluid delivery systems where you're going from a fairly high pressure inside the pipes out to a tank or something like that where the pressure is very low. One of the most common techniques for measuring flow rate in industrial applications is a differential pressure technique. Now essentially what this is you put a blockage in a pipe and measure the difference in pressure before and after the blockage. If the blockage is appropriately designed for the fluid viscosity, flow rate, and density, then what you'll get is a pressure difference which is proportional to the square of the flow rate. Now the blockage can be a simple plate placed in a pipe flange with a hole in the plate, or it can be more sophisticated designs such as a nozzle or something that we call a venturi. Now what a venturi is a restriction in the flow. What I do is I start off, I do a restriction, typically this is about 22 degrees, to a straight section of the pipe, and then a slow expansion back to the original pipe diameter. The pressure is measured before the venturi and at the constricted region. Now the advantage of a venturi is that it doesn't cause as much pressure drop as a simpler device such as a simple orifice. These differential pressure techniques are very nice in that there are no moving parts, so they're very reliable and fairly inexpensive. The disadvantage is that they typically have a limited dynamic range or range of flow rates where they're accurate, and they cause a pressure loss in the system. Another type of device which uses blockage to measure flow rate is the variable area flow meter, or sometimes called rotometer. And what this consists of is a tapered tube with a float in the tube. The flow causes a pressure force on the float, which is balanced by the gravitational force. Now we looked at several variable area flow meters when we were at the Omega Engineering Labs. One way to measure flow is with a variable area flow meter. In a variable area flow meter, there's a tube which is narrower at the bottom and wider at the top. As the flow goes up through the tube, it pushes on a float, and some of the fluid leaks by the float. As the flow rate increases, it pushes the float higher and higher in the tube. This is a large unit designed to be used for some sort of fluid. We also have a smaller unit also for use with fluid. And you can see here, again, the wider tube at the top and narrower tube at the bottom. And you can see there's a silver float in here. Now, I've hooked up a unit here that's a gas unit, and I'm going to turn on the air here. And you can see, as I turn on the air, the float, which in this case is a silver metal ball, will move up in the tube. Let me increase the flow rate a little bit more. And here we go. As the flow rate increases, you can see that the ball will reach a stable point, at this point around 40 cubic centimeters a minute. I have here some examples of some rotary flow meters. This is a very large flow meter that's designed for use in large pipes with liquids. And what happens is, as the fluid flows down the pipe, it spins this little propeller in here. And as the blades of the propeller go by a Hall effect sensor, or it could be an optical pickup, it creates a pulse. And what you do is you actually calibrate the flow rate to the number of pulses coming through the system. Now, this one's designed for use with liquid. This is a smaller one that's designed for use with either liquid or gas. And you can see if I blow into it, it'll cause the propeller or rotary vane to spin. Turbine meters can be very accurate, but they have the disadvantage that they normally cause a fairly high pressure loss in the pipe. They also need to be mounted in the straight section of the pipe to avoid errors in the measurement due to turbulence or swirl in the flow. Now there's a related type of flow measurement device called a paddle wheel sensor that we also looked at the Omega Engineering Labs, and we'll go see those now. Here are two examples of paddle wheel type flow sensors. The way a paddle wheel sensor works is the flow causes rotation of the paddle wheel, or in this case an optical pickup with a light sensor. I'm going to take this unit and put it into this flow system I have here. And when we turn on the flow system, the rotation of the paddle wheel causes the pulsing of the red light in your picture, which is the interruption of the optical fiber. That can be calibrated with flow rate depending on the fluid you're using. When a bluff body is exposed to a flow, you'll get vortices, which are effectively small whirlpools, shed off the back end of the body, first on one side and then on the other. Now, you may have observed this phenomena if you've ever canoed. As you drive a canoe paddle through the water, you'll see small vortices shed off of either side of the canoe paddle. Now, the frequency of shedding of these vortices is related to the flow velocity, and we looked at a vortex shedding flow meter at Omega, which uses this principle. This is an example of a vortex shedding flow meter. The flow causes vortices to be shed off this vortex generator, which you can see here in the tube. The vortex shedding frequency is related to the flow rate, and the shedding of the vortices is picked up by an optical sensor located in the vortex generator. There are several acoustic techniques we can use to measure flow velocity. One technique, called the time of flight technique, uses the difference in the speed of the wave as it goes downstream in a flow system compared with going upstream. Because the acoustic wave will go faster as it gets carried along with the flow, we can then infer flow velocity by comparing a wave sent upstream with a wave sent downstream. Another technique we can use to measure flow velocity is a Doppler acoustic technique. And you're probably familiar with the Doppler effect. That's the phenomena that causes the tone of a siren to change as a vehicle goes by you. As the vehicle approaches, the siren will sound higher in pitch, and as it goes away, it'll sound lower in pitch. Now, the percentage and change of frequency is simply the ratio of the speed of approach divided by the speed of the wave. Now, this effect is used in the ship to measure speed through the water in these Doppler speed logs that you can see behind me. The way this works is we send acoustic waves out from the bottom of the ship. One is sent looking forward, another is actually sent looking out to the side. We accurately know the frequency of the wave that goes out. And what we do is we compare that to the wave that's bounced back at us, either off the bottom or things in the water, small particles in the water. By comparing the two frequencies, we get a measured Doppler shift. And by knowing the angle of the beam that we sent out, we can figure out the speed of the either boat through the water, or in this case, since we're tied up at the dock, we're simply looking at the speed of the current underneath us. So you can see right now that there's about a 1 knot current coming from the left and about a little greater than 1 knot current coming from the bow of the ship. Now I'd like to talk about a few of the techniques that are used for measuring the flow of air or a gas. You can probably see behind me several of the anemometers that are used on this ship. Now, for airflow, we need to measure both the magnitude and direction of the flow. So these propeller-based anemometers actually rotate to give you the direction of flow, and the propeller rotation gives you the magnitude of the flow. Now, wind speed and direction is a critical measurement for meteorological applications. And we went up to the Mount Washington Observatory, which was the location of the highest wind speed ever recorded by man, to see how wind direction and flow is measured there. I'm standing on the instrumentation platform at the top of the Mount Washington Observatory. You may be able to hear there's a little bit of wind up here, but it's actually a fairly calm day. I'm surrounded by a variety of anemometers, several rotating vane anemometers over here, a rotating cup anemometer over here. Also, during the winter, you need a heated system because ice forms on the anemometer. So if you look up here, you can see there's a heated pitot system.